Today's guest, Hammad Bashir, was building ASICs in high school to execute vector searches. And fast forward to today, and you guessed it, he's CTO of a vector search company. Hammad is CTO of Chroma. And Chroma is more than just vector search, but it is vector search, but it's also full text and metadata and regex, and it's all on object storage so that it's 10 times cheaper than traditional vector search. In this episode, we get into how it all works. We also get into the local versus production development story. They are running two discrete systems, an embedded and a distributed, that share the same interface, which is incredibly hard to do and makes for a very nice developer experience. So I hope you enjoy this episode of Database School. Please make sure you're subscribed either on your podcatcher of choice or on YouTube. That helps me greatly. Let me know what you think, and let me know if you have any guests that you want to hear on the show. All right, let's get to Hammad. I am here today with Hammad, the CTO of Chroma. Hammad, do you want to introduce yourself a little bit further?
Yeah, I'm the CTO of Chroma. We build a search engine for AI applications. We'll probably get into what that means. But the funny thing about me is my first job actually was not too different than what I'm working on now. Chroma, part of what we do is vector search. And the first job I ever had was building an ASIC for vector search. So in some ways, I have come full circle in working on this specific problem. So when I was in high school in 2012, actually, I interned at a company that was building an ASIC to do vector search. We can get into what exactly that was. And that's kind of what kicked off my fascination with this specific problem, recommender systems, retrieval, search in general, and kind of have been chasing that interest for over a decade now. I worked subsequently at a bunch of Silicon Valley startups and started my own at one point. We were working on 3D reconstruction. At every company that I ever worked on, I felt this problem that the way that teams dealt with their data was really unprincipled. And so the reason I actually ended up joining Chroma and kind of deciding to work on it was because we felt that there was a way to make how people use data in their AI applications more principled in order to make their AI systems more reliable and more productive.
So it sounds like you never got away from your first love, which is this vector search. And how many, if you had to guess, high schoolers were working on custom ASICs for vector search? If you had to guess, what would you ballpark that to be?
I think it was just me and the one other.
I think it was just you.
Yeah, who got the internship that summer.
Oh, shoot. Okay.
Yeah.
And then you went on, I think you've done Snap, you've done Uber, you've done a bunch. And now you're here at Chroma. And you were, I believe you were the first engineering hire and quickly moved to CTO. So talk to me about like the size of the team now and kind of what your day-to-day role is now that you're like full CTO.
Yeah. So I joined as the first engineer. I worked initially on what we call local Chroma, which Chroma actually is both a pip installable, embeddable database, but we also have a full distributed version of the same API. And the idea is that you can kind of grow from one to the other as your application scales. I initially started working on local Chroma, which is more of a database in a trench coat. It's SQLite and some storage engine glued together to present people a very clean API. And that's what we started with, because our thesis was that the market had a lot of people offering different ways to build search for AI applications, but they were all a bit clunky or had hair on them. And we wanted to do something that felt really, really easy to use and that you could get started with instantly. You didn't have to know anything about how to turn on a Docker container or even think about the different setup flows or compiling something. Just pip install, which is something that you already know how to do, and you're off to the races. So I started working on that. And then after about a year, I transitioned to working on distributed Chroma, which is when we really started to grow the team. So the team today is about 16 people. We're actually entirely engineers. There's not a single non-engineer on the team. And it's a completely flat structure. So even though I have sort of taken the CTO job, most of my time is still spent coding. More of my time is now spent on architecture and kind of like weighing in on high-level decisions. But for the most part, I try and stay close to the metal while the team is still relatively small, building whatever is coming next on our roadmap.
Wow. Okay, that's super interesting. I do want to back up because you said many interesting things there. One of which you kind of just like blew past, but seems wild to me. Y'all have the same API powering a local Chroma and a distributed Chroma?
Yeah.
Okay, so those to me are fundamentally extremely different things and sounds really hard to
Yeah.
like let's say have SQLite and Postgres have the same thing on top of them. Like, yeah, you could squint, but is that kind of what we're talking about? A local one is an embedded. You can just like pull it in. We'll call that the analogous to SQLite one. And then the distributed one is presumably some sort of client server running on a bunch of machines, and that's analogous to the Postgres or something else. And they both have this same like interaction interface. Is that right?
Yeah, that's 100% correct. And the reason we did that is very painful. Yeah,
Yeah, okay, good. I'm glad it's not just me. I'm glad to
no,
hear
no, no,
from the actual implementer. Yeah,
no,
that
no,
is
no.
painful. All right, all right.
It's extremely painful to maintain those two surfaces, and oftentimes, the pain isn't just like maintaining feature parity, but maintaining subtle performance parity, right? And so I think people come to depend on all of the implicit guarantees that your system makes, not just the explicit ones. And so we oftentimes think about how can we make the implicit guarantees as close as possible. We don't always do a perfect job, but that is kind of the gold standard, right? Is you should be able to seamlessly transition from one to the other and not have to think about it. And it's worth asking, like, why did we do it this way? And it's when you build for AI specifically or build for language models specifically. I still, in 2025, feel cringe for saying AI. But when you build for language models specifically, you kind of have to think about the workflows that people go through. And so in a normal Postgres database world, right, you don't like iterate on your local data and then push it up to production. That would just be a bizarre thing to do. You don't like create fake users and then like push it. But in AI, that's a very common thing to do. You create a data set locally, you run your evals locally, you curate the data for some knowledge base or some sort of application that you're trying to build. Once the data is performing in a way that you think satisfies your needs, then you are ready to promote that data set to production. And so that's why we kind of built this flow, is so that you can experiment locally, and then once you're done experimenting, you can push up to prod or deploy it wherever you see fit.
Was this flow kind of like a market driven, user needs driven emergent behavior? Or is this what Chroma set out to do from the beginning, was have this shared interface to two fundamentally discrete systems?
No, it's like been there from day one, really, for us. I think maybe the helpful detour to take, and you tell me if you think it's helpful, is like why we started Chroma, and I think that kind of explains the reasoning behind it. So
I love it. I love it when the guests talk. That just makes my life so easy. Yes, take us on as many detours as you want. So why did you
cool.
start?
Yeah, so I think when we started, we're all previously people working on computer vision and general machine learning systems. And again, we felt this thing that I hinted at earlier, which is the way that most teams dealt with their data was extremely unprincipled. But data, we felt, was one of the strongest things you could do to make systems more reliable when you're building with machine learning.
Can I
And if
pause you
you,
there? And can you
yeah,
describe what you mean when you say the way that they dealt with their data was unprincipled? Can you give me just like a super quick
yeah.
example or something?
So let's say you're building like a self-driving car, right? And self-driving car companies are notoriously good at this because they have to be, because it's very high stakes for them to be correct. But there's this process where every day you send out your car into the wild, and it gets exposed to all sorts of new conditions, new environments, new scenarios. And some percentage of that data is useful, right? You can capture some percentage of that new data and say this could be used to further train the model, to further train the systems that tell the car how to drive. This is a process that's commonly referred to as active learning. So you basically, every time you encounter some new scenario, you sample some proportion of that, and then you retrain the model on that. Now, famously in self-driving, if you sample some small percentage of the data uniformly at random, most of your time is going to be sitting around at stop signs or stoplights, right? That's like just a vast majority of city driving. And so it's not that useful. So the question becomes, how do you sample? And that's what I mean by managing your data in a principled way and thinking about your data that you're using to train models in a principled way. So actually the first thing that we built at Chroma that was kind of our first production commercial offering was actually a way to help teams building computer vision systems find out which data points they could train on to make their models performance better. If you squint, that's a very similar problem to what we do now, which is retrieval for language models. It's just that instead of finding the best data to help boost a model's signal at train time, we're now doing it at inference time. But it ends up being the same exact problem mathematically.
So the problem that you're describing is you've got this huge set of real world data, which is by its nature pretty messy. Historically, you would pull out things that were interesting, i.e., left turns, stop signs, four-way stops, that kind of stuff. So you're finding small, valuable data in this huge set of mostly boring stuff. And now what you're doing is you're finding small, valuable data to help, I'm maybe jumping ahead, augment an LLM. So the LLM comes to you and says, I'm doing this task. And Chroma says, great, let me go out to the haystack and find a couple of needles and give them back to you. And then you can decide if those are helpful. So that's the same kind of problem solution, just in a different space. Is that right?
Yeah, exactly. And it ends up being that vector search is like just the primitive that you need to do that really well.
And so when you all were doing this original computer vision stuff, and so was your solution to making data principled? Was it this like work locally, push remotely, or like how do those two things come together for like the founding story and this I say it with all the love in my heart, crazy idea to do embedded and distributed with the same like layer on top?
Yeah, I think where it comes from is a sort of an understanding of what that workflow really looks like in terms of when there is like a machine learning team, right? Machine learning teams usually have someone that is sitting in a Jupyter notebook experimenting, and then they have someone else who kind of manages the data at scale in production. And those two people work together, but they don't necessarily work on the same thing at the same time. And so we always felt that if you kind of gave someone who is the data analyst role in this specific, setup, the tools to do their experimentation and to perform what they need to do, but then you gave the infrastructure person the tools to do their job very effectively, and then you gave them ways to work together, that you could build a workflow tool that was more than just a database, but actually like a data management system inside of a company that helps them iterate on their data over time, which we think is like fundamentally a little bit different than how you just think about having a database or having a corpus of data. But how do you version that data, which we can talk about some of the features we've built to support that. We have this feature we called forking, so you can like fork a data set really cheaply. How do you version your data? How do you make it easy to kind of know what data is, most useful to like use at a given time, which is the different search offerings that we give. And then also, how do you make it easy to move data from one place to another, off my laptop into the cloud, and that sort of a thing. Because oftentimes the like latency considerations of doing something locally are so beneficial, and also having the data locally for other reasons is very beneficial, right? I don't want to just look at my data in one tool. I want to slice and dice it over a bunch of different tools that I'm used to using in my notebook environment, and then I want to push it up to some other environment that is kind of where my production system runs. So I think that sort of insight on how machine learning teams were often structured is what gave us the confidence that we should build the tool to kind of support people scaling from just getting started all the way through to deployed. That's one reason. And the other reason is also most developers don't want to mess around with having some sort of clunky setup when they are just getting started. They just want to type in, I have problem, get me solution. And so just making Chroma the easiest thing to use was another motivation to have this local embedded database.
So I'm in my head, I'm getting a picture, and I want you to tell me if this is right, that the person who's working with the data locally is kind of an artist as much as they're a scientist, because it feels to me like you're describing this person is like using their Jupyter notebooks, they're in their office, and they're like basically exploring. They're navigating, they're trying to figure out, all right, how am I going to work with this data? What types of characteristics does it have? What's the shape? What's the useful stuff? And then finally they land on something that feels like, hey, this might be a hit here. And at that point, then they, you keep saying push or promote it to production or live data distributed system. And then that's when they can start to use it in the real world. So is it right that like this person that's using everything locally is basically an explorer trying to figure out, is this data any good? And if so, how?
Yeah, yeah, totally. And like the word that I think the sort of like literature word for this is like exploratory data analysis. So like commonly when a data scientist or someone sits down, the first thing they do is understand their data or look at their data. And that process that is commonly called exploratory data analysis. And that's kind of one of the number one things we encourage our customers to do when they come and they ask us like, how do I make my search better? It's, have you looked at your data? Have you actually sat there and combed through everything that's happening and understood, what exactly is going on? And it sounds so banal because people are expecting all these like crazy magic toolbox tricks, which some of those exist and they're useful. But until you've kind of just done the painful thing of sitting at your laptop and clicking through every data point, understanding how the language model is choosing to grab some piece of information versus discard another, and really getting an intuition for how the system is performing, you're just not going to be able to use all these like higher order techniques. And so we invested a lot of time into how do we just like get people to look at their data, which is why we also built like a really, really nice dashboard. So like part of like using Chroma's distributed product, which we call Chroma Cloud, when you buy it from us, is like just you get a dashboard that's extremely powerful. You get all the search features, and we're continuously expanding that surface area to try and make it so that people can just look at their data in a much better way. Because most people don't. They just kind of put their data in and they go, why is it not working?
Yep. You know
Yeah.
what this reminds me of, and I'm gonna miss some of the particular details. You know that famous like reading of the scrolls challenge where they found all of these like charred scrolls and they tried to use computer vision to read them. Do you know what I'm talking about? What is
Yeah,
that?
yeah.
Is that Nat Friedman? Who was
Like,
that?
yeah, I think it was like the Vesuvius scrolls or something.
Vesuvius. Yes,
Yeah,
that's it. I was thinking Pompeii. Vesuvius is right. And one of the kids that won was like 16 or 17, and they did an interview with him, and they're like, "So how did you do it?" And he's like, "Well, I sat down and I just looked at it for a really, really long time, and my eyes started to get used to it." And that's always stuck with me, where it's like sometimes you just got to look at it for a really, really long time.
yeah.
So I want to talk about first. First, I want to talk about the mechanism by which you promote from local to cloud, because I'm curious if that is like or rather, I'm curious how that is a first party like primitive implementation. But then I want to roll back after we talk about that and talk about, you said the local one is a couple small tools and a trench coat put together with some glue. So then I want to talk about that. But this whole like get it off my machine into Chroma Cloud, what's the flow for that? And how like easy is that? Because since you own both sides, I assume y'all put a lot of thought into it.
Yeah, so basically the way that it works today is we have a CLI. You can kind of use the CLI to browse data as well as do other things. One of the things that you can do with the CLI is push your data up from any local Chroma DB to the cloud database environment. Right now, the way that happens is actually fairly naive because most of the people iterating on data locally don't have data sets that are materially large enough that it's worth doing anything fancy. And sometimes the simple solution just works. And so we actually end up just kind of bulk copying the data in an efficient way. There are things that we've discussed doing that I think maybe are more interesting to people listening to a database podcast, which is the underlying storage engine for Chroma Cloud is kind of akin to a B tree. And we could, in the future, there are ways for us to kind of intelligently manage the way that we copy the data over to basically just read it out of the underlying storage engine in local in like an ordered key value way, such that we're basically just copying it from one key value store to another. And there's ways to make like B-tree copying and bulk inserts really efficient. So that's like a thing that we've thought about in the future, but the market demand for like having very large data ingest from local to cloud has just not really been something we've seen. Most people are iterating on fundamentally small data sets, and we can talk about this maybe a little bit more in the context of Chroma Cloud, which is most AI data sets are actually not that large, and that's kind of initially what we really built for, was instead of having like one very large ginormous index, which is traditionally what vector search and many search engines in general optimized for, both in research and in industry. But AI applications instead have like millions to hundreds of tens of millions of smaller indexes. And the challenge moves from how do you have one giant index to how do you page these like smaller indexes in and out of memory. That's not to say that the big indexes aren't important and that we don't support them. But I think that workload shift is really what makes existing kind of solutions that people were using a little bit clunky or hard to deal with. And that's one of the reasons that we started Chroma. Was just when we were doing this computer vision stuff, everything else we were using just kind of fell apart or was clunky or difficult to use, which is really how we ended up working on this specific thing. So the copy from local to cloud is today a very naive thing, but could definitely be optimized in the future.
Okay, I changed my mind. We're going to go cloud first because you teased me, you got me, it worked. Okay, so you get the data from local to cloud, small amount of data. Where does the okay, I'm going to lay out a few and then you get to pick. All right, where does the rest of the data come from if not pushing from local to cloud? I assume some sort of production systems are dumping stuff in. That's just a guess. And then let's talk about the actual kind of structure of how all of that data is stored and how you're creating these indexes, what type they are, and how you're executing operations against them. So you pick. Start somewhere with any of those, but it's dealer's choice.
Yeah, I mean, I think we can maybe just walk through what adding data to distributed Chroma or Chroma Cloud actually means, as like the way to kind of discuss this. So when you push data up from local to cloud, or if you just ingest it from some other place, the first place that your writes actually go is to a write-ahead log. And so we have a log. Chroma is entirely built on top of object storage. And the reason it's built on top of object storage is that the economics that you can deliver with object storage are so powerful compared to traditional search systems. You can literally be 10 times cheaper if you build on top of object storage compared to putting all data on live replicated NVMe SSDs. And so when you first write to Chroma, we write to a write-ahead log that writes to object storage. And the way that that write works is we have a 100 millisecond buffer of time where all writes get batched for a given collection. We call like one logical unit of query in Chroma a collection. So for example, if you were building some sort of customer support bot, you would have all of the records for that customer support bot in one collection. And so we basically keep a 100 millisecond window open. You write for 100 you keep this 100 millisecond window open, you get writes accumulating in the 100 millisecond window. The reason we do this is to amortize the per operation cost in S3 or GCS or whatever your object storage is. We then flush that entire 100 millisecond unit of data into what we call a fragment, which is kind of put into a strictly increasing sequence number. And that strictly increasing sequence number is basically like slots in any sort of replication log. You can think of it that way. So if you were writing like the 26th fragment or the 26th time that data had been batched in a 100 millisecond window, we'd write that to object store and flush it. That ends up being extremely high throughput. And then we, after that, update what we call the manifest, which keeps track of where all of these fragments live and where they are. And there's a couple failure conditions we can get into there, but basically that gives us a way to get a strongly consistent ordered log built on top of object storage. And that's only possible because all of the object store providers and Amazon actually only as recently as December 2024 released compare and swap or conditional primitives. So you can do compare and swap style algorithms on top of object store. So when we write fragment sequence number 26, we know that nobody else can now write fragment sequence number 26. So our log is concurrency safe. And so we can get concurrency safety through conditional operations on object store because the providers now all support compare and swap primitives, to support conditional operations, so we can do compare and swap style algorithms.
I have some questions about that whole process, but can you describe that offering from the cloud providers a little more? So what did they provide that prevents it from being able to overwrite slot 26?
Yeah, so if you are using an object store, your two primary APIs or three primary APIs are get, put, and delete. Get a key and get the associated value with the key, put a key with the value, and delete a key with the value. The new offering that the providers are giving is the ability to do that conditionally. So you can say put if not match. And the thing that you're matching on depends on the exact object store that you're using, but let's just say it's like a version number. Or like a hash of the data. And you can say like, if the data has changed since I viewed it, you should invalidate my operation. And so that lets you do, opportunistic optimistic concurrency control style algorithms where you do some work locally, speculatively, and then you write back to some source of truth. And if the world has changed out from underneath you, you just abort and roll back. And these primitives allow you to do those sorts of algorithms. And so we use that all over the place. We use it the most for our log. And the reason we built the log on top of object storage, besides just delivering, lower storage economics, is also because we can just get really, really, really high throughput. So Chroma, when we onboard a large new customer and they're like migrating all of their data, we just add more log nodes and it kind of auto scales up. And we can get tens to many, many higher GBs of throughput across log nodes. So we can very quickly saturate one log node entirely with again in terms of its throughput to S3 before we end up ever hitting any sort of bottleneck on the customer's end or becoming a bottleneck
Okay.
on the customer's end.
So the cloud providers introduced, so historically you would have had to get it, read it back, do something on your server, and then put it, which of course is wide open to timing issues. Now you can basically do an upsert with object storage, and you can decide. Can you decide, hey, if it's changed, block, or if it's changed, update? Do they give you that, or is it just like if it's changed, bail?
Yeah, I mean, it's basically if it's changed, bail.
Cool.
And then you
Okay.
kind of have to decide what to do. So it's like put if match or put if not match style
Okay.
behavior.
Cool.
Just yeah.
So what you just there at the end called log nodes, I assume that is so that's a server somewhere that your customers are just hammering with data. On that log node, you've got this 100 millisecond timer, and you're catching a bunch of that data, and then when it hits 100 milliseconds, you flesh it out to S3. And I believe you said that you do that because the S3 requests could get cost prohibitive if you're trying to do it, and it's also probably not very performant. Trying to do it every time somebody sends you a little bit of data, and 100 milliseconds of data, honestly, that's very small. So they're really hammering that log, that log node.
Yeah.
And so every 100 milliseconds, you take what you've received, package it up, and throw it across to S3, and S3 stores that. And now it's in the storage, it's safe. And so these log nodes you can scale up. S3 is infinite, so you can just continue to hammer it as much as you want. Once it's in S3, you've got these slots, and then you've got a manifest somewhere that maps slots to some other probably metadata or something. Then what happens? What happens next?
Yeah. So then what happens is we have what we call compactor nodes. And basically the storage engine of Chroma, as I mentioned, is akin to a B tree. There's some differences in terms of how we lay it out, but it's conceptually, and we can get into why a B tree too, by the way. I think this is an interesting discussion in the context of vector indexes. But it's laid out as a B tree, and basically what happens is compactor nodes pick up these log records asynchronously, and they get notified through a notification mechanism that some collection is dirty and needs to be compacted. There's like a scheduling policy that kind of ensures that we are being fair across tenants. The system is multi-tenant, so tenant fairness is something we take quite seriously in the design. And so there's a scheduling policy that kind of tries to control which nodes are able to compact any given data at any given time. These compactor nodes, basically all they do is build indexes. And they build these indexes on top of a key value storage engine, which is B-tree-like. And basically all of our indices, you can think of them as inverted indexes. So if you've ever seen like an inverted index in like a full text search engine or any sort of key value search engine, our vector search indexes are also just inverted indexes. And then we also now support what are known as sparse vectors. And those sparse vectors are also just using an inverted indexed style approach to be queried. So basically everything to the storage layer just looks like I have inverted indexes that I write to a key value store. And we have a system that basically the compactor nodes pull from the log, they then build these indexes and then flush them to object storage. After they flush them to object storage, that's again like this pattern that you'll see all over the place in our system design, is we write to object storage speculatively, and then we go update some consensus source of truth. So after we write to object storage, we then go update what we call the sysdb, saying that I flushed these files and this new version is live and ready for the rest of the cluster to use. These are the compactor nodes they flush, and then they update what we call the sysdb. The sysdb is like the catalog. It is kind of keeps track of what indexes exist, what collections exist, where the files are, what tenants are there, and then we have this unit of grouping we call databases. A database has a bunch of collections inside of it, akin to like create database in Postgres. And basically, this sysdb gets updated with the new version. And once it's in the sysdb, the rest of the cluster can be aware that these indexes are ready to be used. And in the meantime, the way we get strongly consistent reads is you basically pull from the log and you just read from the log and serve reads from there. So we do deliver strong consistency because we always have data durable on the log the minute you've received an acknowledgement from us. And the sysdb is actually just a Postgres database. It's nothing fancy. We call it, it's internally the control plane of the system, and we basically write to it. And the reason that it's useful to have that as a SQL database is before, because Chroma existed before the cloud providers offered these like put if not exist primitives. And so specifically before AWS allowed it. And so we used the sysdb as a way to transactionally ensure that only one compactor wins. Because it's possible in certain, scaling scenarios or failing conditions that two compactor nodes pick up the same collection and both do that work. We lose some resource usage because we do some wasted work, but then when you update the sysdb, again, optimistic concurrency control, only one is going to win. And that kind of design pattern is all over the place, similar to how the log first writes a fragment and then it updates the manifest. It's conceptually a similar thing. And then after these indexes are built, they go to query nodes, which we can talk about.
Okay, thank you. Yes. Okay, hold on. This is awesome. I'm going to try to walk you back through it because there's a lot there, and I want you to help me along the way. So don't be shy. So at this point, we've got all this stuff written to object store, and the compactor nodes come through. Now, the compactor nodes are not actually changing. When you said compactor nodes, I initially assumed they were picking up what's on object store and like compressing it or rearranging it and then putting it back. But that's wrong. The compaction, which is from where it gets its name, the compaction is it picks up a set of these logs off of S3. And then the compaction is the creation of the index. That's why it's called a compactor node. Is that fair?
Yeah, and it kind of comes from LSM terminology. So like if you kind of squint, we have this like LSM style architecture where we write to a log, we like build some in-memory state, we then periodically like compact it into an index and then flush it to object storage, which looks a lot like a LSM style like log, memtable, final actual ready SS table data. So that's where the word compaction comes from.
Perfect. That's very helpful. Okay. So then these compactor nodes have all this logic around them to make sure that everybody is treated fairly because you all are managing data for many, 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 many different tenants. And it's not like I'm running this in my own AWS. So you're handling all of this and you've got these heuristics to make sure that we're, treating everybody fairly. You pick it all up, you turn it into this index, and then you go, these compactor nodes walk over to the sysdb, which is Postgres, and they say, I've got is it still slots? Is it still like, hey, from slot 26, I grabbed all this data and compacted it? Or have we lost that association at this point?
No, that's entirely correct. So like the way the whole system thinks about the world is just like, where in the log is my data? And we're just kind of saying like, based on the sequence number in the log, up to what point are you, right? So when a compaction occurs, it says I've compacted up to this point. And then at any point when you then go to read, you know that you have a compaction from here. And then if you want to get a strongly consistent read, you just need to go a little bit ahead of that in order to get the rest of the data that maybe was recently written.
I see. Okay. So it walks over to sysdb, says, I've just finished compacting. Here is the compacted data. And sysdb is just serving as a system of record or pointers. And then the compactor writes that compacted data back to S3, but not, overwriting. It's writing it somewhere else. And that's where those inverted indexes are stored. And then sysdb is just now the manager of who's got what where. Is that right?
Yeah, you can think of the sysdb as like the file system. Like it basically just knows where everything is actually laid out in physical storage and then presents like a logical abstraction for other services to talk to that kind of say, here's where you need to go to access the data. Yeah.
And so are we up to date so far on everything you've described? I got close enough. We're good. And we can go on to querying. Is that, did I do okay?
Yeah, that's how you write to Chroma.
Okay, perfect. That's how you write to Chroma. I just hit some API and I don't worry about it. Okay, so then I want to, let's say give me a domain. Am I doing transcript search? What am I doing here that we can walk through a querying operation?
Yeah, let's do transcript search. Like, let's say you have a bunch of podcasts. Maybe you're like some sort of research analysis. You're doing some sort of research analysis on podcasts. You have a bunch of podcasts indexed inside of Chroma, and then you query for like, tell me all references to vector search on Aaron's podcast.
Perfect. Okay, so that's what we're doing. So somebody's gonna say, I've got, let's say, I'm a Chroma Cloud customer. I've got all these transcripts in Chroma. Somebody comes to the website and they're like, I want to get all of the references to vector search and like the surrounding text a little bit, maybe just the podcast episode, whatever. Search API request fires off to some AWS endpoint. Then what happens? You said query nodes earlier. I assume that's where we're going. But what happens when they hit it with vector search? That might be confusing because we're talking about vector search. What happens when they hit that endpoint with the word Postgres? Walk me through that from there.
With the word Postgres? What do you mean?
So their search query is Postgres instead of vector search. Because if we are searching for vector search in a vector search, we're going to lose the audience. So they're searching for the word Postgres.
Yeah, they're searching for the word Postgres in all these podcast transcripts.
All these podcasts.
Yeah. So what happens then is we have a routing layer that knows what collection you're trying to talk to. That routing layer basically hashes you to a query node. That's it. So all it's doing is it's like,
collection is what? Is that like Aaron's data is, or like Aaron's podcasts? That's so a collection.
Aaron's podcasts would be one collection.
Got
what
it.
You're searching over, what your corpus, that's your collection.
Okay.
And so what we do then is we basically say, you're talking to this collection. This collection has been assigned using a hashing scheme to some query node. And we do authentication and all that fun validation stuff. We then route it to a given query node. That query node basically has like a 3-step process. It first checks if the data is in its local cache. So if the data is already in its local SSD-based cache, then it basically can proceed. If it's not, then it will go to object storage and fetch that most recent data that came out of the compactor node. Once it does that, it knows it's at this sequence number. It knows I'm at like sequence number 26. And then it checks with the log and says, is there any data ahead of 26 that I need to know about? And reads any data from 26 up to now in time in order to deliver a strongly consistent read. After it pulls that data down, it basically merges those two subqueries together, both the like compacted data query and the log query, and then it returns that result back up. So concretely, like for the search term Postgres, what would happen is if you were doing vector search, we would receive this vector, and we may be helpful to talk about what a vector is at some point.
Yeah, but, like, and I'm glad we didn't stick with vector being the word we're searching for. Okay, so you receive this vector. Okay,
you receive this vector that encodes the word Postgres, right? And maybe you're also using full text search on Chroma because that is something that we also support, and it's useful for targeted queries like this. Vector search is not always the best solution, and so you give us a full text search query and a vector search query in hybrid, and that comes in and basically gets searched against both of our indexes, which are inverted indexes, right? So for vectors, what'll happen is we'll find some region of this vector space to look at, and we can talk about how that region identification works, but we find some region and we just look at that region and like compare other vectors, where if two vectors are close to each other, they're probably related in some way or semantically similar. So maybe we find a reference to like the previous podcast with someone who had worked on like the Postgres storage engine, and that comes back. And then the full text search scan also hits an inverted index, and that is literally just like going to be the term Postgres pointing to the list of all documents that contain the word Postgres, and it's going to pull that out. It's going to merge those two things together. You can actually specify like some way to rank those, like how do you want to combine that. It combines those two results sets together and returns them back to you. You now have a list of a way to find every document that mentions Postgres or something similar, and then you can do whatever upstream you want to do with that. Maybe you give it to like a language model to decide to like write some summary of all references to Postgres on the podcast.
And so to clarify, that's what I'm getting back from Chroma is here are all of the relevant documents with some sort of presumably unique ID that is inside the collection, and I can go fetch them again. That's the result I get back? Okay. And do I get back, let's say it's an hour-long podcast, and we talk about the founding story in the first like 2 minutes. Do I get back some sort of like guidelines on how that where that appears in the document, some sort of chunk range, or how do I do that part?
Yeah. So the way that we suggest people to do that is, so maybe backing up for a second, when you do vector search, you are first using what we call like a embedding model, a model that takes some sentence or a piece of text, or now any modality of data, could even be a video or audio, and turns it into a vector. And this vector has this property that if that two vectors are close to each other in some, let's say, 2D space, that they are somehow semantically similar. Right. So if you had the words Postgres and SQLite, those are probably very similar, but the words Postgres and race car are probably not very close in semantic space, right? And so that's all this vector is. And basically what we do at that point is we kind of check to see if there are like any when you're actually embedding that data, the embedding model has a fixed window. So when you actually get this embedding, when you have this text and you're trying to turn it into an embedding, there's a fixed window that the embedding model can support. So what people commonly do, and you kind of hinted at this, is you have to break your text up or break your video up or break your audio up into chunks. And that has to be fed into this embedding model in a way that it is like, up to some max size. And there's many different approaches to decide how to break the data up to feed it into an embedding model. And so when you actually get data back from Chroma, what we're giving you back is these chunks, right? So you might actually just get the snippet of audio that like says Postgres at minute 1, if you have like some transcript of the audio. And maybe that's not very useful. So what people could do at that point is what we see customers often do is we support metadata search. And you kind of have to combine all of these search primitives together to build something that actually really works. There is no out of the box, just like get great search, although we're working on that, we think. And so you basically use metadata search to basically tag each chunk by saying like, this is the actual podcast that it was recorded in. This was maybe the start minute and the end minute. And then when you get back this, maybe your search strategy is to then expand out of that region and find other documents in that area, right? And maybe you want to recreate like the local region where that reference occurred. So you basically know where in the transcript that specific talking point occurred, and then you can expand out and decide what else you want to look at in that chunking area. So that's commonly how we see people do it.
When we're talking about document retrieval, we're not talking about my PDF document that's 60 pages. We're talking about the chunk of that PDF document, the chunk that has been run through the embedding model, and those embedding models have limited capacity. And so we chunk 60 pages down into maybe 120 chunks and then send those over the wall. And then what Chroma gives back is chunk number 1, chunk number 58. And then on my side, I do some sort of metadata matching decision making. Do I want to include chunk number 2 and 57 and 59? And then that's kind of up to me as the application developer. But you've said, hey, here's where those needles exist in the haystack. What you do with them at this point is up to you, but I went and found them. Is that right?
That's correct. Yeah, and I think where it's now getting interesting is initially this all used to be like handwritten. People would kind of say like, I'm retrieving the language model gets asked some question. Human writes code to like take this question and give it to like the search system. The search system is like, handwritten by a human to do full text search and metadata search and vector search and maybe regex search, right? And all these different search things. And they compose in a human defined way and upfront what the search strategy should be based on their application. And what's interesting is this is starting to change. People are now increasingly doing, and this is no stranger to anyone who's used like deep research or Claude Code even. They're starting to do what is being known as agentic search. So you basically just like give all of these primitives to the language model, and you just say, you're in the driver's seat now. You decide what to do, right? So you look at the data that comes back, you look at the metadata, and then it writes the next turn of search. And it does this iterative process and decides how to best search the data. And I think that's increasingly going to be the way that people build their search systems going forward. The like days of like hand tuning search to like be specific for your workload, I think that'll always be there to some extent. But I think this like agentic search loop where you just basically say, no, you language model have the capacity and the ability to go through and just iteratively search through a corpus and make something better and better, make a search better and better over time, just because you can understand the way that the data is structured and laid out, is just going to be something that works a lot better. So yeah, this whole process where, you have to think about, well, like, how do I get the chunk and how do I combine them? I think if anyone at home is listening and like getting overwhelmed by like that proposition, like I think increasingly agentic search is the way to think about building a thing that works almost just as well a lot of the time, but has a lot less complexity for you as the application developer. Um,
Come on,
in,
there's
in
gonna be
getting,
nothing left for us humans to do. Now it's taken over the hard
yeah,
parts of doing search as well.
yeah,
Okay,
yeah. They're
no,
coming for the search engineers.
I'm fine with that. That's fine. I want to talk about this vector search and how y'all have implemented that, but unfortunately, you've led me into a great segue into what is my spiciest question for you: is RAG dead? Because listen, I spend too much time on Twitter, and every Tuesday, RAG is dead, and every Thursday, RAG is back, and it's just all so exhausting. So tell the people what RAG is, and please, for the love of God, give us a reasonablest answer to is RAG good or bad or dead or alive or the best thing or the worst thing ever?
Yeah, it's a great meme, right? I think that's why.
Oh, gosh, it's brutal.
Um, yeah. Um, I think the right way to think about this in earnest is to ask what RAG is, because I think that's what
Mhm.
most people are debating when they say, is RAG dead or is RAG not dead? So maybe
Shocking that people are talking past each other on Twitter.
on
This
Twitter,
is
it's crazy,
surprising
right?
to me. Yeah, I'm
So if
shocked.
you just to like maybe explain what RAG is, RAG stands for retrieval-augmented generation. Um, I think initially the term comes from a 2021 paper from a team at Facebook AI Research. And basically the idea is you have, in their parlance, like two ways of encoding information or two possible ways of many of encoding information in a like AI system. The first is what they call parametric memory, and the second is non-parametric memory, which is a fancy way of saying a learned model and a search engine. And basically the idea is
Is that like what it was trained with, what it's built into the weights, and then other data you can add in?
exactly. So I have some model that I have trained on a bunch of data, and it knows stuff because it's memorized it, or compressed it, or make whatever learning argument you'd like to make. And then I have some search system that has access to information, and I can retrieve it, right? And that's just information retrieval. So the idea would be that you could take this generative model that has the capacity to, generate new pieces of text, and combine it with this non-parametric search system, this system that's not really learned, although now there are ways to make them learned. So you take this non-parametric search system and you basically use information retrieval techniques, right? So you just like basically use Google, and you take this data and you give it to a language model so it can generate information. And that's retrieval augmented generation. That's all it means. So, and this is like a very common paradigm. Like everyone building AI applications does it in some flavor. Because language models are very expensive to train, they're also not like predictable to train. I can't like reliably insert a new piece of information into a language model. And so the current way that people are getting around this is they basically just use a search system or an information retrieval system, and then they augment the generation of that language model with the search system in
Because
order to,
importantly, language models are dead once they're trained. They're fixed, they're static, it's
yeah.
just there. And so if we want to add in new business information or new up-to-date information or old stuff it wasn't trained on that we found in a library somewhere, it's just like the weights are what they are. You got to add it somehow. So we're doing this, we retrieve it from somewhere, and then we give it to the LLM, and then that uses that data to augment what it's going to generate back for us. Good?
Yep, that's
Okay.
correct.
All right.
Yeah.
So is it dead?
Um, I, I think I have like there's like the whole like show me the incentives and I'll show you the outcomes. So I have an
Please. I
incentive to
love
be fair
this. I
to
love
tell you
this.
to
Yeah.
tell you that it's gonna exist. But despite that, let me make my most unbiased argument as to why I think it's something that will always exist. I think that if you look at it, if you just look at it on a basic level, language models are not going to get any easier to train and inject information into, barring any large architectural advances. There's like there's nothing that tells us that that's immediately around the corner. And basically the entire field of deep learning for, however long it's existed now, it doesn't have an answer to this question of like how do we reliably inject new information in a deterministic way without either forgetting old information or mutating existing information in ways that we can reason about, right? And so if you want to build systems that are reliable and don't make things up or don't get things wrong or don't say things that they don't actually know, you have to have some system that can basically like provide that grounded truth. right? And I think that grounded truth will come from real world data that has been curated by, I don't want to say humans because it may not even be humans that curate that data, but has been curated by intelligences that have direct access to the ground truth information about what's going on, right? So if you like are reading some legal proceeding and you witnessed as an intelligence, I'm not just going to use that word as opposed to like human or AI. If you witnessed as an intelligence like this legal proceeding, you maybe have ground truth information that like a language model somewhere else does not, right? And so if you can give that information to another language model, that's just always, I think, going to be a thing at a high level. Like structurally, most of the economically valuable data in the world is siloed. Like it's not like you can train on all of it. I don't think that's possible. There's no path I see to getting all of the economically useful data and giving it all to one language model and maintaining that process. I just don't see that. Right. And so there's both an economic and kind of structural reason why you will always have to have like some amount of data that's just held out from train time, right? And then there's also a kind of just functional reason as to why you want these systems to have ground truth data and not just be trained on everything, and barring any architectural advances. Now, the argument that's always made counter to this is, well, the context windows are getting bigger, and eventually the context window will be so big that it just won't matter. And I think I just have like a fundamental matter of, have you done the math on that question? Because today the largest the largest context windows that you can get are 1 million tokens. Now, the kind of like rough heuristic is one token is roughly 4 characters. So let's just be kind of naive and say that it's ASCII and it's 4 bytes. So I have 1 million tokens is 4 million bytes, so 4 megabytes. Okay, so right now in 2025, I can put 4 megabytes in my context window. Not that big. Um, and okay, now scale that up 100x. So now you can store 400 megabytes. That's still not that much. And so just like on just like a mathematical basis, it doesn't make much sense. And then all the laws of normal, like I have memory, I have disk, the storage hierarchy still come into play, right? Because how do we actually do inference today with today's current architectures? You have to move all that data through memory. And so if you need to move it, let's scale it up 1000x and say it's 4 gigabytes, right? If you need to move 4 gigabytes through memory every time you want to answer a query, I just don't think there's a way to make that, both from a latency perspective and like an economics perspective, viable. I can't use one machine for multiple customers in a reliable way. I have to like pin you to a specific inference node. And these things all work if you make a certain set of economic assumptions. I'm just not bought into those economic assumptions, right? Like if you think that language models, are truly just going to like replace humans, and like companies' purchasing model will be like, I pay this employee X tens of thousands of dollars a year. I'm going to like have a box that's like dedicated to them and like is like my AI employee. Maybe that works, but that's not how we've built software for, a very long time now. We don't like have like some dedicated machine that like serves a single purpose. Like everything is pointing to the opposite, which is as much abstraction in between you and the fact that the machines exist. Right? This is like the whole serverless push. Like a lot of just like cloud abstractions are kind of designed this way that you as a developer don't think about the fact that there is a compute layer. You kind of just have an API and you are happy with that interface. And so those two trends kind of butt heads for me, where somehow I'm going to have this like system that has this really large context window, and the only way to make the math work is either by paying a lot or by sacrificing on speed, or I'm gonna have to have some system that basically can scale out, scale down, move users from like one node to another very cheaply. And I think the only way I see to do that right now is with search systems. I don't see a way to do it without search systems if you want personalized data on a given workload. And this isn't like to say that approaches that try and continuously train models will not become common. I think that will become extremely common. That like people will personalize small models or even medium-sized models on given customers, and there's already like empirical proof for this, right? Like all of recommender systems work this way. Like the largest at-scale deployment of continuous learning is arguably systems like TikTok. right? And they already continuously, yeah, it's terrifying when you think about it. And they already like retrain a model. If you go, like, read the little bit that they've disclosed publicly about how these systems work, like every few interactions, some lightweight small model is getting, or it's not like literally a deep neural network that gets trained at a different frequency, but some XGBoost like style model is getting trained at some frequency, and that's how recommender systems have worked for a long time. And so it's not inconceivable to me that that's how these other systems will work. So in short, I don't think RAG is dying. I think that it will always exist in some way. And I think that people just, if you follow the incentives of the people who are saying these different things, you start to kind of see why they might be saying what they're saying, which is true of me too, right? Like I'm obviously going to tell you that the thing that I'm dedicating n hours a day to is like extremely valuable in the long term, but I just don't see a path to work around it right now from an engineering perspective. If there was one, we'd be working on that.
Yeah, that is true. Dedicating n hours where n is, I'm sure, a very high number. Tell me about context rot. So is that like, so this whole, and I know that like talking heads on Twitter are just trying to get clicks and likes, so I don't take it very seriously. But is that where some of this RAG is dead? Is like, well, it was a non-careful application of putting too much stuff that you retrieved into the window, and now the thing is freaking confused. And they'll say, oh, see, RAG just leads to context rot. My view as a naive outsider is, well, you retrieved too much stuff that didn't matter. So like you filled up your million token window and now it just looks at the first 250,000 tokens and you're mad. So what is context rot, and is that just a misapplication of RAG, or is it something fundamentally different?
Yeah, so Context Raw is a research report that we put out earlier this year that basically studies how model performance degrades as you add more information to the context window. And we do a couple different experiments, simple things like having it repeat a word and seeing at what point it starts to fail, all the way through to like, what if we do like needle in a haystack style experiments with different distractors. And I think the generic thing across all models was that as you made the information landscape that the model is processing inherently more confusing or inherently more conflicted, it did worse.
It got confused.
Yeah. And I don't think this is like some like it's I think to everyone who read it, it was like, yeah, this is something that we're seeing all the time, and aligns with us, and it's good that the team at Chroma did some empirical validation of this fact. But I don't think it was a mystery to anyone who is working with these systems all the time. And
they felt it, like they felt the vibes of the more like I shove in, a 150 page PDF and it never returns anything from chapter 10. I wonder why that is. Yeah, we feel the vibes, but y'all did the research.
Yeah, but that's like if I asked you to like sit down at a table and gave you 20 minutes to read 150 pages and said like, hey, like, tell me the answer to this fact. It's inherently a hard problem. And so I think that if you're willing to like kind of anthropomorphize for a little bit and say that like language models have some level of the context window is like working memory, right? Then you can kind of think of retrieval systems as long-term memory, where you can go and pull information out that has existed for long periods of time, or that maybe need to be considered carefully without getting confused. You and I would get confused too if we sat down and like read through thousands of pages, and immediately were asked to like with high confidence deliver an answer. It's just like inherently a difficult information processing problem from an information theoretical standpoint. And so I think that problem will just always be hard. And I think the jury is out on like how good we can get at it in terms of being fast. But I think the search system being an integral component to just like reducing confusion is just always going to be a performance optimization, right? Even if you have some system that is really good at just like ripping through very large context windows, it's probably going to be more expensive, at least for the foreseeable future. It's probably going to be a lot slower, at least for the foreseeable future. And, it's probably going to just like end up being a lot worse than if you had just given it the same information, but curated down to what it really just needed, right?
So going back to our podcast search earlier, if I go and I ask an LLM, hey, give me all the podcasts where Aaron talks about Postgres, and I give it every podcast I've ever done, it's going to perform worse than if I do an initial elimination of podcasts that are about SQLite and we never said Postgres even one time. And so, is that what you're saying? Is like, hey, this context windows are getting bigger, but as you described, they're really not that big. But if you fill up the whole freaking thing, that is just a lot of stuff for it to look through. So let's do an initial elimination pass using some sort of search, and then feed in the context and give that over. And the rot is way, way less, if not hopefully eliminated altogether.
Yep, I think that's the right way to think about it. And where I think it starts to get a little bit interesting is I think having like small domain specific language models is something that we at Chroma are big believers in. That like you can have like a small model that does a task really, really well if it's like a narrow task. And what's interesting is you can just run those a lot faster. So I think the like platonic ideal is, what if you could do a very wide fan out initial single state search, and then normally you have like all this like re-ranking that happens in a search system, right? So you do vector search plus full text search, you do this like hybrid re-ranking, then you run it through like a learned re-ranker. These are like the normal stages of search. And I think that is potentially at risk of, dare to use the word, but like being disrupted, where instead you just use very small, very fast language models, and you just rip through the data very, very quickly. Right. And so like the current language models, the large ones run at about 100 tokens per second or 100 hertz. It's not inconceivable that in the next year or two, we'll have language models that run at 15 to 20 kilohertz. You can already get like 1 kilohertz on like a GPU at home with a small model, right? And so we are seeing a huge increase in the speed at which models are going to run. And that really changes how you think about language models in your search stack. And so that's really where our head has been at in terms of how we build over time, is how can we start to move language models from being this thing that just consume the data into being things that participate in the actual search itself at a low level.
Oh man. I thought we were moving fast. I didn't realize we were moving that fast. I'm not, I'll be honest, I'm not ready for that yet. So I don't know what I'm going to do in the future, but at least it'll be exciting. At least it'll be fun. I'll tell you what, I'm glad we started with cloud, because the podcast is over and we didn't even talk about local. We spent all our time talking about cloud. So here's what I want you to do. One is I want you to come back at some point, because we need to talk about local. We need to talk about hierarchical, navigable, small world. I wrote it down because I know HNSW, and there's like no chance I'll remember the actual thing. Yep. So there's a lot more that we need to talk about. And so you have to, I'm putting you on the spot, you have to promise you're going to come back at some point so we can talk about some of the other stuff. And then I want you to finish by telling us who should look at Chroma, what business use case, what pain, what is the ideal user experiencing right now where they come to Chroma and they're like, oh, thank God. And then finish by telling us where people can find and follow you on the internet.
Yeah. So if you are building an AI application that needs to search over data, and you have very large volumes of data or small volumes of data across many different customers, Chroma makes that exact setup both 10 times cheaper, but far, far, far easier to operate. So if you don't want to wake up in the middle of the night to a page about your search cluster failing to scale, you should definitely come check out Chroma Cloud. We designed it to be the easiest possible thing to run for ourselves, but then also to run in service of our customers as a search system that scales in the way that AI applications scale. And then also, if you are building AI applications that need to be able to kind of leverage all the different search tools, from regex to full text search to vector search to metadata search, in order to deliver like really high quality search and combine these in a very neat, clean, easy to use API, then you can sign up at trychroma.com and get started. And we're also building some things in the future that I think I kind of hinted at today that will be quite interesting to people as we continue to grow the product. And then,
before you give us all your social handles, who designed trychroma.com? Because it's cozy and I love it. It's like clean, but it's not sterile. Who did that?
Yeah.
Is that y'all in-house?
Yeah, it's in-house. It's actually a lot of it was Jeff, our CEO, who designed it.
No way.
Yeah.
Yeah, he seems like a hip, cool guy, so that doesn't surprise me very much.
Yeah, he is
Yeah,
great.
y'all go check it out. It's like clean and kind of industrial and scientific, but it's not cold and sterile. It's got the nice, warm, kind of cozy feeling. So good job, Jeff. Way to go. All right, where can the people find and follow you on the internet? Oh, and are you hiring? Do you need anything from the listeners? Do you need open source? Do you need people to send in resumes, or probably not resumes, but like proof that they're actually geniuses? Like, what do you need from the dear listener, and how can they find you?
Yeah, so you can follow us on at TryChroma on Twitter, or if you want to follow me, I'm at Hammad Time on Twitter. And we are hiring across infrastructure and database storage, which I think is probably something that people on this podcast would be interested in. If you're interested in both how do we scale to hundreds of clusters across the world, both like BYOC style deployments, but also just like managed deployments, and building the machine that builds the machine, please do reach out for infrastructure roles. And then if you're interested in the latest and greatest in query execution, the latest and greatest in storage engines, we are, I think, pushing a lot of the boundaries on what you can do in terms of building a modern search storage engine and query execution layer. So please do reach out. We're hiring for those two roles very, very actively, and already have a great team that you would be joining and getting to work with. So we'd love to hear from you.
Awesome. Amazing. Thank you for doing this, Hammad, first of all. And I did catch it live on air that you said you're going to come back. So gotcha. And for the dear listeners, thank you again for tuning in. This is absolute delight for me. Please reach out and let me know what you think of the episode. Please share it far and wide. Tell your friends, tell your enemies, tell everyone. And then also tell me who else should come on the show. I've had great luck with serendipity of people reaching out. And if you're listening to this and you're like, hey, I'm smart too, don't be shy. You got to reach out and say, I've got this thing I want to talk about. Let's talk about it on the show. That is amazing. I love that. I will always receive cold pitches from smart people. I will always delete cold pitches from PR people. So if you're listening and you're a PR person, forget about it. But if you're a database engineer, I want to hear from you. So please do everything that all good podcasters say to do, like, subscribe, I don't know, whatever else. But I'm glad you're here listening to Database School. And Hammad, thank you again for doing this.